Good morning students. Welcome back to your chemistry class. Today we are going to do some numericals based on de Broglie's equation and on uncertainty principle, Heisenberg's uncertainty principle. If time allows, then I am going to do some more points on quantum model of an atom, because tomorrow I shall begin with quantum numbers, right? So just now, to begin with the numericals, let us start with the numericals of de Broglie's equation. So the first numerical says that a proton whose mass is equal to 1.66 into 10 to the power minus 27 kg is moving with kinetic energy 5 into 10 to the power minus 27 joules. What is the wavelength of proton, right? So let's do the solution of this. We know that wavelength is equal to what? Planck's constant upon under root 2em. How do we get this formula? When we are talking in terms of kinetic energy, then we use this formula. So we know that h, that is Planck's constant, is equal to how much? 6.626 into 10 to the power minus 34 joules second, right? Then what else do we know? The energy, kinetic energy, is given how much? 5 into 10 to the power minus 27 joules. And what is the mass given? The mass given of a proton is 1.66 into 10 to the power minus 27 kg. So what have we to do? We just have to place all these values over here. So putting all the values here, what do we get? The wavelength is equal to h, that is 6.626 into 10 to the power minus 34 upon under root 2 into what is E? 5 into 10 to the power minus 27 into 1.66 into 10 to the power minus 27. Okay. So how do we solve this? I hope you all know that when we remove this under root, all these become square, and hence this will be equal to 6.626 into 10 to the power minus 34 whole square upon 2 into 5 into 10 to the power minus 27 into 1.66 into 10 to the minus 27. You solve all this and you get lambda, you get wavelength equal to 1.62 into 10 to the power minus 7 meters. So what did we calculate? This is the wavelength of the proton, right? I hope this is very clear. It is completely formula based questions, right? We move to the next numerical. An electron beam emerges from an accelerator, right, with kinetic energy 100 electron volts. Okay, what is its de Broglie's wavelength? So, and in the question it also gives the mass of electron, which is 9.1 into 10 to the power minus 31 kg. Okay, then your Planck's constant we already know, 6.626 into 10 to the power minus 34 joules second. Then what else do we know? In the question it gives 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. Okay, this is provided in the question. So let us begin how to solve this question. Right, so write down the formula first. That is, wavelength is equal to h upon under root 2 em. Fine. Now we know that kinetic energy, it is given what, how much, 100 electron volts. Okay, and it has to be converted to joules. So this will be equal to 100 into 1.6 into 10 to the power minus 19. So this will be equal to 1.6 into 10 to the power minus 17 joules. Followed? So now place all the values here. So your wavelength is equal to 6.626 into 10 to the power minus 34 upon under root 2 into what is your E, 1.6 into 10 to the power minus 17, and mass is given to you 9.1 into 10 to the power minus 31. So when you solve all this, what do you get? The wavelength will be equal to 1.228 into 10 to the power minus 10. Clear? So these are all formula based questions. Let's take one more question. The third question, it says calculate the momentum of a particle, right, which has a de Broglie's wavelength of 2.5 into 10 to the power minus 10 meters. Okay, so let us do the solution of it. We know momentum, that is P, we had studied yesterday, is equal to Planck's constant upon wavelength. Okay, so let's go ahead, calculate the momentum. You have to calculate the momentum. So 6.626 into 10 to the power minus 34 upon what is the wavelength given to you, de Broglie's wavelength, 2.5 into 10 to the power minus 10. Okay, so your answer comes out 2.64 into 10 to the power minus 24 kg meter per second. I hope de Broglie's equation, numericals based on them is very clear. They are all formula based questions. Now we are going to move and do some numericals based on Heisenberg's uncertainty principle. So let us do the fourth numerical. This will be based on Heisenberg's uncertainty principle. It says, on the basis of Heisenberg's uncertainty principle, show that an electron cannot exist in the atomic nucleus, and it gives the radius of the nucleus is given to you as 10 to the power minus 15 meters. The mass of electron is also given to us as 9.1 into 10 to the power minus 31 kg. Okay, and your Planck's constant is also given 6.626 into 10 to the power minus 34 joules second. Okay, all these points are given to us in the question. So let us solve this question. What does it say? That the size of the nucleus is given. Okay, the mass of electron is given, and it says that on the basis of Heisenberg's uncertainty principle, we have to show that electron does not exist in the atomic nucleus, right? So let's write over here size of the nucleus, that is the size of the radius is given to us. How much is it? 10 to the power minus 15, right? So let us suppose over here that the electron exists in the nucleus. Then delta x, what is delta x? That is uncertainty in position will be equal to how much? Will be equal to 10 to the minus 15. Fine. Therefore, I can also say that delta x is equal to 10 to the minus 15 meters. Now, we know that delta x into delta v is greater than or equal to what? Planck's constant upon 4 pi m, right? So, delta v is greater than or equal to h upon 4 pi m delta x. What have you to do? Just place the values over here. So, greater than 6.626 into 10 to the power minus 34 upon 4 into 3.14. Pi is 3.14 into what is the mass of the electron given to us? That is 9.1 into 10 to the power minus 31 into what is delta x? Just now I wrote 10 to the power minus 15. When we solve all this, what do we get? We get delta v, that is the velocity of the electron, is greater than 5.77 into 10 to the power of 10 meters per second. So is it possible for an electron to reside in the nucleus whose velocity is 5.77 into 10 to the power 10, which is much more than the velocity of the light? No. Therefore, we can say that an electron cannot exist in the atomic nucleus. I hope this is very clear to you. So, I'll write it down over here. Don't worry. You will. So, since the uncertainty in velocity delta v is greater than the velocity of light, okay, which is not possible, hence electron cannot reside where? In the atomic nucleus. I hope this is very clear to you. Okay, we move to the next question now. The fifth question says that the uncertainty in position and velocity of a particle are 10 to the power minus 10. This should be in meters, and 5.27 into 10 to the power minus 24 meter per second respectively. Okay, calculate the mass of the particle. Now, what does the question say? The uncertainty of the uncertainty in position, and what does the question say? The uncertainty in position is 10 to the minus 10 meters, and uncertainty in the velocity is 5.27 into 10 to the power minus 24 respectively. We have to calculate the mass of the particle. So what do we write? According to Heisenberg's uncertainty principle, right? Delta x into m delta v is equal to what? H upon 4 pi, right? We have to calculate the mass. So mass will be equal to how much? H upon 4 pi delta x delta v. Now place all the value. 6.626 into 10 to the power minus 34 upon 4 into 3.14 into how much is delta x given to you? That delta x is uncertainty in position, that is 10 to the power of minus 10, and delta v is uncertainty in the velocity, that is 5.27 into 10 to the power minus 24. When you solve all this, what do you get? The answer, that is the mass of the particle, will be equal to 0.099 kg, right? So these were some of the numericals that we have to understand and do. Some numericals I'm going to send you in the assignment. Well, tomorrow I will start teaching you the quantum numbers. But before I start teaching you what are the quantum numbers, today we should understand some important features of the quantum mechanical model of that atom. Okay, so I'll write down all the points. This is just the revision of what we have done till now, so that tomorrow when I start with the quantum numbers, it becomes little easy for you to understand. Okay, so I'm writing down over here important features of the quantum mechanical model of atom. Right? Now, quantum mechanics, it is a theoretical science. It deals with the study of the motions of the microscopic objects. Remember, not macroscopic objects. Microscopic objects that have both wave-like and particle-like properties. Okay. Now, quantum mechanical model of the atom, it is just the picture of the structure of an atom. Okay. The important features of this model I'm going to mention over here. So the first point that we need to remember is that the energy of the atoms is the energy of the electrons in atoms is quantized. And what do we mean by this word quantized? It means that the energy of the electrons in atoms, they have only specific values. And what was that specific value? For hydrogen, if you remember, it was minus 1312 upon n square, and for any other multi-electron atom, it was minus 1312 upon n square into z square. Do you remember all these points? So that is what I am going to write over here. The energy of the electrons in atoms is quantized. Okay, so the energy, what was the formula? Minus 2k square pi square m e to the power of 4 z square upon n square h square. Do you remember this? So this was equal to minus 1312 upon n square into z square kilojoules per mole, where over here what was z? Z was your atomic number, which could be 1, 2, 3 and so on. Or for hydrogen atom, it was minus 1312 upon n square kilojoule per mole. This was for hydrogen. This was the first point. Okay, now the second point about the model, that is, this model provides the most probable region in the atom where there is maximum probability of finding electrons. So this region where there is maximum probability of finding the electrons, it is termed as what? Atomic orbitals. Okay, this model does not specify the exact position and the momentum of the electron, and therefore we can say that this model is in accordance with the Heisenberg's uncertainty principle, right? So I write over here, this model provides the most probable regions in the atom where there is maximum possibility or probability of finding electrons. Okay, these regions are termed what? These regions are termed atomic orbitals. So we have come across new word, atomic orbitals. So what is the difference between orbital and orbit? I will teach you after this. But first let us understand all the important features of this model of an atom. Clear? So this model does not specify the exact position and the momentum of the electron. This model does not specify the exact position and momentum of the electron, hence is in accordance to Heisenberg's uncertainty principle. I hope the second point is very clear. Now, coming to the third point. The third point about this model is that the atomic orbital is always described by a wave function. Okay? And this wave function, there may be many wave functions which are responsible for an electron. So, there are many atomic orbitals also in an atom. In each orbital, the electron, it has a definite energy. An orbital cannot have more than 2 electrons, but in multi-electron atom, the electrons, they are filled in various orbitals depending upon their increasing energy. Fine. So I mention over here that an atomic orbital is described by what? As I told you, described by wave function. Okay, and wave function, how do we write it down? We write it down like this. So since there are many wave functions, since there are many wave functions, therefore many atomic orbitals are also there in an atom. Orbitals are there in an atom. I hope this is clear. Okay, then an orbital cannot accommodate more than 2 electrons, right? In multi-electron atom, what happens? The electrons are filled in various orbitals depending on the increasing energy. Coming to the next point, that is, let me rub this, then I'll tell you. The fourth point says that the probability of finding this electron at a point within an atom, it is always proportional to the square of the wave function, right? So what does that square of the wave function mean? It also means that there is electron density there, and this electron density is always positive. It is possible thus to predict the region within an atom by finding the value of the square of the wave function at different points where the electron will most probably be found in that atom, right? So the probability of finding the electron at a point within an atom is proportional to the square of the wave function. Okay, this wave function, square of the wave function, this square wave function is also known as electron density, and it is always positive, always positive. Clear? It is possible thus to predict the region where within an atom by finding this value of the square of wave function at different points where the electron will most probably be found. Then coming to the fifth point, a wave mechanical model, it always provides three constants. What are those three constants? The N, L and M. And these N, L, M, They are the quantum numbers. So over here, n means the principal quantum number, L means the azimuthal quantum number, and your M means the magnetic quantum numbers, and they specify the position, energy, and the orbital of the and the orientation of the electron in an atom. Clear? So wave mechanical model provides three constants. What are they? As I told you, N, L, and M. Okay, which are known as quantum numbers. Okay, they provide, or maybe they specify the position, energy, and orientation of the electron in an atom. So I hope all the points are very clear to you about the quantum mechanical model of an atom, and thus tomorrow we shall begin with the quantum numbers. Now, to end up with this video, as I told you, we came across a new word, orbital. So here I want to specify to you what is the difference between an orbit and an orbital. After that, I will wind up with this video today. So let us understand the difference between orbit and orbitals. Okay, so what is orbit? It is a well-defined circular or the elliptical path around the nucleus in which an atom revolves. This is what you have been studying since class 7. So it is a well-defined circular or elliptical path around the nucleus in which an electron revolves. Whereas then what is an orbital then? It is the region in the space around the nucleus in which there is probability of finding the electron is maximum. That is called as orbitals. Okay, so it is the region in space around the nucleus in which probability of finding the electron is maximum. Okay, come to the second difference between orbit and orbital. These orbits, they are circular or elliptical, whereas the orbitals, they have different shapes. Like for example, the s orbital, it is going to have a circular shape. P orbital will have a dumbbell shape. Then d orbital has a double dumbbell shape. F orbital is not in your syllabus just now. The shape is not in your syllabus. F is there, but the shape is not in your syllabus. Thus, all orbits are circular or elliptical. Okay, whereas orbitals have different shapes. Like there are s orbitals. S orbital, as I told you, is circular. P orbital is dumbbell shape. D orbital is double dumbbell shape. Okay, and F orbital is there, but that shape is not specified, or you may say it is not in a syllabus. Coming to the third point of difference between orbit and orbital. Orbits, they are always directional, and orbitals, except s orbital, all others are directional. So orbits are non-directional, and over here, except s orbital, all others are directional. Okay, then the fourth point of difference between orbit and orbital, very important, that is orbit can accommodate maximum of 2n square electrons. Okay, whereas the orbital, they can accommodate maximum of 2 electrons with the opposite spin. Fine. So an orbit can accommodate to a maximum of 2n square electrons. Okay, where n, you know what is it? It is the principal quantum number, or the number of shells till now, just what you know. Whereas over here, the fourth point about orbitals, what did I say? That an orbital can accommodate maximum how many electrons? 2 electrons. Okay, with opposite spin. So it can be shown like this. If you remember, if you have seen somewhere, this is what we are going to study from tomorrow. Okay, then the fifth point of difference between the two, orbits, they give a definite path to an electron. Therefore, they are against uncertainty principle, whereas orbitals, they do not represent a definite path. They just represent a region in the space where there is probability of finding electron, that is also anywhere. Thus, it is in accordance with the uncertainty principle. Okay, so orbit gives a definite path to an electron. This is against the uncertainty principle. Whereas, what did I tell you about orbitals? Orbitals does represent a definite path. It in fact represents a region in space where the electron may be present anywhere. Thus, in accordance with uncertainty principle. Followed? And the last point of difference between the two, that is orbitals, that is orbits, they are planar. It considers the motion of an electron in a plane, whereas orbitals, they are three-dimensional motion. They give three-dimensional motion to an electron around the nucleus. Okay, so this is the last point of difference between the two. The sixth point, it says, as I told you, orbit is planar. It considers the motion of the electron in a plane. Okay, whereas what do we know about the orbitals? It gives a three-dimensional motion to the electron. Gives three-dimensional motion to the electrons around the nucleus. Okay, around the nucleus. So that is all for today. Now tomorrow I shall begin with the quantum numbers. Thank you.